Okay, yes. It's also the same thing as 1 to the x to the negative 1.
Let me think. Actually, last time we were here.
That's not the same thing as x to the negative 1.
Yes, 1 over. I'm sorry.
1/2.
1/2.
Yeah, let's do a couple different things.
I knew that, though, seriously. I knew that. Stick to it. Your test is still messing with my mind. It's going to be my excuse for the rest of the time.
So I wanted to, last time I stated the Taylor's theorem, but without proof, and even without justification. So it probably seemed kind of mysterious, right? But just so that we all are aware of it, we saw it. But I decided to go ahead and do one more example where we can see where the coefficients come from. Okay. I'd like to find a Taylor series for this. I'd like to figure out a number to put right here, and another coefficient right here, times x plus some other number right here to say that's times x squared, and so on and so forth, and hopefully get a general pattern. At least that's the hope. And finding coefficients that would make this polynomial look a lot like this, right? Would be finding a Maclaurin series. That would be called a Maclaurin series, right? Yeah.
One more thing. So this only works for the geometric?
Depends what you mean by geometric.
So the x squared, x cubed, right?
Yeah. So if these are all ones,
Right.
then it would be geometric. Like 1 plus x plus x.
Okay.
That's geometric.
Okay.
But if the
Just
coefficients
for
are anything
all-
other than ones,
All the power series,
yeah,
Oh, okay, okay.
yeah,
Tracking, sorry. Should have missed that day.
yeah.
It didn't help. I was here. Didn't help.
You get that 1 point.
But like now, as stated, I don't think that there's such coefficients are going to exist, and the reason why is because this would be a Maclaurin series or a Taylor series centered at 0. Okay. And if you think about what the square root function looks like, it looks like that. If I'm looking for a series centered at 0, the radius of convergence would have to be
0?
because there's no graph over here to the left of 0. You see what I mean?
Mm-hmm.
So yeah, so like this it wouldn't work. But what we're going to do, what I want to do right now, is find a Taylor series centered not at 0, but at 1. That is to say, I still want to find a constant to put right here. I still want to find a constant to put right here, but it's going to be in times x minus 1. See that? And instead of an x squared right here, it's going to be x minus 1 squared. And instead of an x cubed, it'll be x minus 1 cubed.
And the only reason we're saying that is because this function, without that -1, the convergence sign would be 0.
Mm-hmm. Yeah. I'm going to call this first coefficient, the constant coefficient, I'm going to call that one A0. The second coefficient, I'm going to call that one A subscript 1, A subscript 2, and A subscript 3, so that the subscript corresponds to the power of x minus 1. And this next line, I'm just going to repeat exactly what I have written up here, but just to have some more practice at writing in sigma notation. In all of these cases, it always falls into the same pattern. going to find, I'm going to go ahead and like, again, kind of tell you what we're going to discover, and then we'll see why it is. What we're going to find in a few moments is that a sub n is going to, the formula for a sub n, and we're going to show this, is going to be the nth derivative of this function, which happen, in this case is a square root function. Evaluated, last time we met I said it was evaluated at 0. This time?
1.
At 1. So the formula for this one is not too different from the formula that we had for the Maclaurin series.
So it's pretty much where it's centered at, is what you're valuing
Yeah.
the derivative.
So not that much of a change.
So theoretically, if we have a question like this, it shouldn't be that much harder, right?
Yeah.
Theoretically.
Yeah, he's gonna find a way though.
There's always a way. Yeah, but let's see why. So we'll set that aside, pretend we don't know it.
Okay.
And I'm dealing with a function right here, right? Let's just do this in general, I guess. But what I'm going to do is I'm just going to plug in 1. Let's see what you get when you plug in 1. Notice if x equals 1, it says that f of 1 equals
0? Well, a equals a
Almost.
sub naught. Yeah.
almost always.
Yeah.
Almost always. If I plug in 1 for x, it looks like all these terms are going to become 0, but when you bear in mind that one of these terms is x minus 1 to the 0 power, that one's not going to disappear, but all these are going to become 0, 0, 0, and on down the line. So it's literally going to become a0 plus a bunch of zeros. So for any Taylor series centered at 1, you can safely say that the constant coefficient will definitely be the function you're interested in evaluated at 1. For the square root function, a0 will be
1.
because the square root of 1 is 1. But I'd like to know what all the rest of these coefficients are. How am I going to do that?
Take the nth derivative.
Yeah, so I'll start with, we'll do a couple of steps just to see what's going on. So for this series, you can see that this is always a constant. The n is actually a constant, right? It's lots of different possible values. For each term it's a different value, but and each individual term is a constant. So constant multiple rule says the derivative of each term, I can set aside the constant. But the power rule says I got to bring down the n. The chain rule says keep the inside the same. Power decreased by 1. And then the chain rule also says take the derivative of the inside.
Multiplied by the,
Yeah, the derivative of x minus 1 is just 1. So there you have it. But there's a subtle detail that's often missed when you're using sigma notation. It's a little more clear if you write it out like this. This term, when you take the derivative of the first term, that one
0.
disappears. And that's the only one that disappears.
Disappears or 0?
It's a 0.
Okay.
Yeah. Yeah. And so because you're adding 0, we can pretend it disappears. But for the rest of them, for the rest of these, the derivative won't be 0, right? But you're, in this case, you'll be bringing down a 2. In this case, you'll be bringing down a 3.
Right, right.
Decreasing the power. So that's why it's a really subtle point. But whereas before I was starting at 0, now I'm starting at 1.
Because that would be 0.
Yeah. So I play the same game. I plug in 1, and I learn something new about the function. I see that when I plug 1 into the derivative, I'm plugging 1 into this series, and every term except for one of them will become a 0. The only one that's not a 0,
it's a sub 1.
yeah, it's the one where you have x minus 1 to the 0 power, right? It's a 0 power when n equals 1, that's the first term. And so that's going to become a sub 1 times 1 times x minus 1 to the 0 power. And in conclusion, I can see that a sub 1
Equals 1.
f prime of 1. All right?
Oh.
Yeah. So we'll do just a couple more and try to extrapolate from there. But yeah, you can see from right here, let's see. Let's try this again. Take the derivative again, term for term. Pretty much the same pattern will fall out. You're going to have, we already have these coefficients of a sub n times n, but now this particular derivative of this, we're going to use the chain rule and the power rule, bring the n minus 1 down in front as a multiple, and we're going to decrease the exponent by 1.
N squared minus n.
Yeah.
Or you can leave it as
There you have it. And this one is going to work for every term except for one of them.
A sub 2.
Yeah, because the first term in this series is a constant. And it'll be 0. And we're just going to say, well, since we're adding 0, we'll just ignore it and start at 2 instead. So now evaluating it at 1, I can see that f double prime at 1 is, oh yeah, sorry, I got carried away. Almost all of these terms are going to be 0, except for the term where the exponent is 0. That is to say, when n equals 2. That's the first term. And the first term would be a sub 2 times 2 times 1 times 2 minus 1, I should say, right? So a sub 2 is equal to f double prime evaluated at 1 divided by 2 times 1.
2 factorial.
Yeah, it might seem silly me writing this 1, but if we go through this, like, you know, several more steps, you're going to start to see a factorial to emerge, right? And so we might be at the point now where it's starting to become believable that this formula, why this formula is the way it is, right? I guess I might edit this to make it more explicit and say this is really over 0 factorial. And this is really over 1 factorial. I'm gonna stop here and maybe I'll try to think of a better explanation for that.
My bad.
Yeah.
Well, the good part is we talked about a bunch of nonsense.
Yeah.
How's that good part?
Because then he could cut out that whole block and no one will know. You know what I'm saying? That's
Yeah.
the good part.
Sorry, the guys came late to class today, so I didn't.
Yeah.
Sorry. Anyway, what I want to say, okay, so this is suggestive of why that formula is true.
Right.
What I'd like to do is, like, there's a really important theorem in mathematics called binomial theorem, right?
Yeah, I did not understand that.
It's actually something that could be taught in pre-calculus, but it's pretty powerful.
Right here, dude. I tried to read that last night, and I have no idea what it's talking about.
Well, like in this particular case, right? If I want to do like, well, let's see here actually. Maybe I'll do a simpler case. Yeah, let's do it. Let me start with a simple. Before I do the square root one, let me do something simpler. Right. This is more like the binomial theorem. So, like, for example, if I have something like this, if I have like x minus 1 to the 4th power, let's say.
Right.
That's considered a binomial?
Yeah. Well, this inside the parentheses
Okay.
is a binomial.
Yeah, but then all out is just
Yeah.
huge polynomial, right?
Well, I can use the Taylor's theorem here, right? See, what I want to do is I want to express this as something plus something times x plus something times x squared, and so on and so forth, right? And it's not that bad. In fact, because these are just x's, this is going to be a Maclaurin series, a Taylor series centered at 0. And so,
Wait, why would it be centered at 0?
just because I have x's instead of x minus 1.
Oh, right, yeah.
But that function is the w, ain't it?
Could be. This one is like a, if you know what the x to the 4th looks like,
Yes.
it's not a w though. It looks like a parabola with like a kind of flat at the bottom.
That's what I mean.
Yeah.
As you expand it, you can get, okay, cool, yeah.
So, in this case, I can see that f at 0 is
A dot, A sub 0.
1.
That would be negative 1 to the 4th power, which is positive 1. So therefore,
So A sub 0 is 1.
that's 1. And if I take the derivative, get that, what is the derivative evaluated at 0?
Negative 4.
Right? And, oh, I erased it. But when, so that second term is when n equals 1, it's going to be divided by 1 factorial. So this is going to be a negative 4.
Oh, what?
Yeah.
You're gonna run out of numbers on this. I guess you go negative when you get to like the 5th one.
Well, let's cross that bridge when we get there. All right?
Positive 12.
Well, now you get natural
Yeah, so squares will be positive. Positive 12.
I think just keep going.
Right? But by that formula,
Can't do it on 0.
the next coefficient is not going to be 12, right?
It's just 1. Huh?
Notice the next coefficient is not going to be 12.
Yeah. Because you got to bring down the 2.
Yeah, because it's the second derivative divided by 2 factorial. Josh learned that the hard way on test.
So like 6?
Yeah. Yeah.
Hmm?
6?
Yeah. So,
But I learned it. And that's all that matters.
yep. So positive 6 now.
Right.
And then? You have 4 times 3 times 2 times x minus 1 to the 1st power.
Right.
And if you plug that into 0 into the third derivative, you're going to get
24 divided by 3, 8.
so negative 24. Yeah, divided by 3 factorial.
Oh, negative 4, I'm sorry.
Yeah. So, that's going to be a negative 4. And likewise, we'll do the 4th derivative.
So there's a factorial in the front.
Mhm.
Right.
Give it 1, huh?
Okay.
So that's 1 times x to the 4th.
Right.
And there's technically infinitely many more terms after that, but from this point forward, the derivatives are extremely easy to compute. The 5th derivative of this,
0.
that's
Oh,
0.
and so the 0 has to stay there. So it'll just be 0 the rest of the time.
So it's plus 0x to the 5th, plus 0x to the 6th, plus 0x to the 7th.
Forever.
Yeah. So this is a case where the power series actually terminates. But, but look at this. I've managed to expand this without actually expanding it.
Right.
I didn't have to FOIL anything out, right?
Yeah.
I could have, and that's what you would get if you did.
Oh, really? Yeah. That's pretty cool.
But yeah, this works it's pretty universal because it even works for square roots.
Say what?
Yeah, if you flip that, it is that. So
If you flip what?
if you actually did
Oh, you're saying it's
x
back-
minus
yeah.
1 times x minus 1 minus x times 1
Yeah.
minus 1, it actually does come out to no. Yeah, x to the 4th.
You said no.
Plus
Yeah.
minus 4x cubed plus 6x squared minus 4x. And I was always taught to put the I6 digits to the left.
So that's where it comes from.
Yeah, sort of. I mean, this is actually, I think, an unusual way to show the binomial theorem. It can actually be done without Taylor series.
So then here's a question.
Yeah.
Going backwards then.
Mm-hmm.
So given the 1 minus 4x plus 6x minus 4x cubed, right?
Mm-hmm.
To get to that, how would that go then? I mean, how would you do that from the, yeah,
Wait, say again? What do you want to do?
from the actual series in which it terminates to the actual binomial?
Yeah.
How would you do that?
Mm.
Do we go with that? Did I miss that? Did I pay attention?
No, we ain't going
Because
to
in that case, I'm like, then what's the point of ever freaking factoring again? You know? Because I was talking to my own guy.
Well, I'm not sure if this is answering your question, but it might be related. Notice that I can say other things too. That's a minus. Notice that everywhere I see an x, I'm replacing it with x plus 1.
Okay.
Which is kind of interesting because now this is just x to the 4th.
Yeah.
And I can see that x to the 4th could be, see here I'm expressing this function
Yeah.
as in the Maclaurin series. Well, now I can use this to express this other function as a Taylor series centered at -1.
Oh, -1?
Because look at this, that's x plus 1.
Right.
That's the same thing as x minus -1. X minus -1. So this is a Taylor series. For x to the 4th power, centered at x equaling -1. So lots of things you can do. Lots of sleight of hand going on here. But yeah, like, but right here, you know, if I know, what I can see is that if once I know all the derivatives of this, then I really got a good idea of what's going on, you know. So for instance, like, in this case, f of x is the square root of x. So the thing I originally had in mind was finding a Taylor series centered at 1, right? So I plug in 1, I get 1.
All right.
The derivative, using the power rule, you get that. You plug in 1, and you're going to get
1/2.
that. Yep. The second derivative, think of this as 1/2 of
Negative. Yeah.
that. That's going to be
Negative.
1/2 times negative 1/2 times x to the negative 3/2. But when you plug in 1, you're going to get,
1/4.
yeah, I'm going to write it like this. I'm going to write it as negative 1/2 times 1/2. I'm just going to leave it like that.
Times negative 1/2 times negative, or positive 1/2 times. It's just gonna keep doing that.
No, because you have 3 halves right there. So then it'd be
3/8.
2. No, 5/8. Okay.
Why would it be 5/8? 3/8?
So double negative, so it's going to be positive this time.
I'm going with the exponent. 5 halves.
Right.
Right.
So in the next step, when you find the next derivative, I think I'm starting to see what's happening here.
I am definitely not so
5 halves. 1
Yeah.
half, 1/2, 3 halves, 5 halves.
So the negative is going to make it negative. It's going to switch. It's going to be alternating. But yeah, but there's going to be an extra 5/2 attached to this. It's going to be a negative 1/2, 1/2, 3/2, 5/2. I think this first 1/2 is kind of an exception to the rule. But for all the rest of them, you see how we have these consecutive odd integers, and we always have 2's on the bottom.
Right.
Right?
So 2n plus 1 over 2.
Yeah, and you can see how the whatever the degree of the derivative is,
It's 1 higher.
if it's even, the answer is a negative. If it's odd,
So
it's
negative
positive.
1 to the n
Mm-hmm.
times 2n.
And don't forget, we also need to divide by n factorial. Right. So in general, so in this particular case,
You say n divided by n.
so for this particular function, the nth derivative is going to be negative 1 to the n. Right, that makes sense, because now if n is even, well, that would make it positive. When n is even, I want it to be negative, like this, right?
Yes.
So let me put a plus 1. Okay, that should do it. Just offset it.
Well, oh, so 1/2. Okay, 0, then 1. Okay, yeah.
Mhm.
Oh, 0.
And
Starting at what though?
I got to do, yeah, that's interesting. How do I write that out? That's kind of the difficulty. It's going to be, oh, yeah. I'm deciding if I should tell you about semi-factorials.
Nope.
Not yet.
Yeah.
All right, so it's going to be like so starting at, so in this case, when n equals 4, I want to try to find a formula for this, the largest number right here,
Okay.
right? Which would be
2n minus 1. No, 4. That'd be 8.
2n minus 3.
2 minus 3, yeah.
So how about, let's say it like this, 2n minus 3, and everything that's smaller than n by 2. Oops, minus 5, I guess I should say. You just keep going, right? until you get down to 5 and 3 and 1, right?
What?
Yeah, what?
Yeah. Oh, okay, yeah.
No, what?
To where he's going to he gets right there and not include the negative 1/2.
What?
I guess I'm writing these numerators in the opposite order.
Yeah.
1 minus 3 equals negative 1. Okay. 4 minus 1 equals negative 1. 6 minus 3 equals 3. 4. Okay, I guess, yeah.
Yep. Actually, you know, it looks like there's a 2 for every single one of these.
All right.
I could just put a 2, 2, 2, 2, 2, and 1 extra 2 right here. 2. And that's all over in factorial. Okay, that formula is not, it's kind of an eyesore. But let's just write out the first, let's say 4 or 5 terms of this series and see what it looks like. Okay.
Okay.
So, in other words, I can now see that square root of x could be rewritten as 1 plus what? 1/2 x minus 1. Right? Minus
1/2.
Yeah, and that's divided by 2, right? Oh wait, no, f prime. This is f prime. That's 1/2 over 1, right? Over 1 factorial. So minus,
1/2.
that's a positive 1/2. This is positive 1/2, right?
Yeah, F prime.
Plus 1/2. Wait,
But
hold on.
the-
Wait, I'm getting myself confused.
Yeah, mister.
This is the first power, so that's the first derivative.
Right.
This is going to be times x minus 1 squared.
And that should be
So I should
Minus.
take this number
Negative.
divided by 2.
so 2 or 1.
So it's going to be
Negative.
1/2.
Divided by 2?
1/4 divided by 2 is an eighth. Half of a quarter is an eighth.
Yeah, you said divided. Doesn't
So,
that mean
yeah.
you multiply by the reciprocal?
So would it be
So
1/2?
you bring the 2 on top.
So when n equals 2, that's the second derivative. Evaluate at 1 divided by 2 factorial.
Right.
So in this case, that would be negative 1/4 divided by 2. We're
Okay,
dividing
yeah,
by.
yeah.
Oh.
And then you flip, okay, yeah.
Mhm.
I thought you said
When I
divided by
factorial.
1/2.
Yeah.
So the next term is going to be attached to a x minus 1 cubed, which is coming from here, right? At this, but it's going to be divided by 3 factorial, right?
Right.
So that is a
2, 4, 6.
all right, 3/8.
I didn't smoke break.
2, 4, 6. Well, would it be so? Okay.
So
is
you're
this
saying
the first
all of
step?
that, that's the numerator, divided by 3 factorial. Is that what you're saying?
No, he's just keeping track of it.
Mm-hmm.
So that 1/2, 1/2, 3/2.
Yeah.
The 1/2, 1/2 don't count. It's just no. They should count though.
Mm-hmm. Talking about this one, right?
Yeah, but I thought you said that divided by 3 factorial.
Yeah. So 3/8 divided by 6
Yeah.
is the same thing as 3/8
20.
times 1/6.
48.
Whoa.
Well, I'm just-
2, 16. 1 over 16.
Yeah.
Okay.
Jesus, Louise.
It's too much number crunching.
Yeah, this is a case where our hope was to find a formula that I can articulate in a simple way. And this one's kind of a difficult one to really state.
I mean, you got 2, then you got 2 to the 3rd, then you got 2 to the 4th. The next one's gonna be.
Or it's just multiplying it by 2.
Well, you can't because
Oh,
2
to
to,
8.
2 to 8. So if the next one is 15 over 16 times 4 factorial?
Yeah. Well, it's coming from here,
Yeah.
and that's
15
yeah,
over 16.
15 over 16.
Right.
And then it's divided by 4 what is it?
4 factorial. So 6 times 4, which is 24.
4, 3, 2. Yeah, the 3 can at least go into the 15. 5 times.
Right. So that leaves 8.
That's all that's going to cancel though. 32, 64, 128. 5 over 128.
Which is the 8th power of 2. So if it goes 1,
You know that for a fact.
yeah, because I do binary. If you go 1, 3rd, 4th, 8th. 8. Yeah, you need to do one more, Mr. Engel.
Yeah,
Just to see the pattern.
well, I'm skeptical that there is going to be a pattern,
Nah,
only
he said
because
you need to do one more. You don't.
We.
experience is telling me not to look.
Not to look.
And the reason why is because I know where these numbers came from. And they had to do with canceling factors, right?
Right.
If I didn't cancel some of these things, these numbers could have been could have been different. Actually, no, I guess they're never canceling the 2. I guess the denominators are growing in a somewhat a predictable way. Like, okay, the 2's here are growing in a predictable way. But when I divide it by n factorial, you know, the next number in I'm introducing could be introducing 3 new factors of n of 2. It could be introducing no new factors of 2. And there's not much of a rhyme. It has to do with the distribution of the primes as to like the pattern at which it feeds these 2's into the denominator.
Then I have a question. Is it not 2 to the n times n factorial
2 to the n times n factorial.
is the denominator, right? Because if 2 doesn't change,
But n factorial isn't necessarily divisible by 2. I mean, it is necessarily divisible by 2, but it's not necessarily a power of 2.
well, no, but the factor that stays the same is the 2 to the n.
Yeah, okay.
So if it was x over 2 to the n times n factorial,
5, 7. Yeah, that's true. All the odds in the top are going to cancel with all the something in the denominator. And
okay, so I did the bottom way to the top. That's not. And then the top would be the 2n minus, well, I don't know if it's 2n.
well, except in this case, there still is an odd in the top.
Well, there will always be an odd. So, yeah, so new money mark real quick. So I can pass this thing on. Know what I'm saying. So if you have 2 to the n times n factorial, that's the denominator, the top. After you get past the what? You get to the 5th or whatever. Yeah, times.
Right here?
Yeah, n factorial. That takes care of all the denominators. Because
That's true. Because that's where it came from.
Yeah.
We were dividing by n factorial.
Yeah.
And it was already like 2 to the n to begin with.
Right.
Yeah, it literally was 2 to the n. So you're right, that will be the denominator. And the top,
So if it's always increasing by 2, I mean, because even at 16, it's supposed to be a 3.
Yeah. So okay, this is what I was debating if I should show you.
Okay.
Get
It's
my
just-
mark out your mouth.
I'm sorry, man. I'm sorry.
What's wrong with you? You better calm down.
What is this nonsense, too?
This is a semi-factorial. All it means, it's no big deal. It just means instead of going down by 1s, you're going down by 2s.
To 1.
All the way down to 1, yeah. Or 2. if this happened to be an even number to begin
If
with.
it stops at 2, then yeah, you can't go.
And that would be right. Well,
How am I
Yeah.
supposed to know that?
I don't know, I just told you. But I mean, if you didn't know that, you would just kind of say, oh, it's all the odd, consecutive odds, you know, something like that.
Okay.
So yeah, that would be your formula for these coefficients. Yeah. And if it's true, then I can fire up Desmos, and if I stop here and just graph that much,
It'll look like the square root of x.
at least close to 1.
Yeah.
At least close to 1. There's going to be a radius of convergence. What's the radius of convergence of this?
Right.
Hey, we can check it. We have ways of checking things like this.
I can check it,
Right? Ratio test.
Oh, wow, yeah.
You know? So from that we can figure out the radius of convergence. But I'm pretty sure the radius of convergence, if the graph looks like this, and I'm looking at 1, so it's centered right there, I know for a fact it's not going to be bigger than 1.
Yeah, it's
It
1.
can't be bigger than 1, right?
Yeah.
So it's probably going to be 1.
Yeah.
That's the radius of convergence. So it'll only look like the square root function from 0 to 2, if that's the case.